Then I'll share the materials with you.
Sorry, sir.
Yes.
Have you noticed the marks on views have changed and they've all just reduced for the quiz that we did, the repeated one?
So there are two quizzes. So there will be two different marks. And then finally, I'll take the mark which is higher for each student.
Yeah. Yes, sir. But the quiz repeat mark was given and then it reduced after a few days. It changed.
Okay, so I think the examiner, she will explain then what happened. Because I'm not marking it. So Dr. Saika Zahan is marking. So we'll ask his opinion that what happened. He will give some explanation.
So it happened with multiple people. Can you just return all our marks back to their original marks? Like
that's not possible. Like I can't tell that because we have to discuss that with the examiner. You understand? I'm not sending the mark by myself.
No,
sir, I am here.
Okay, if you can explain that really, Saika.
Yep, can I share my screen, the solution sheet with the students?
Not at the beginning of the lecture, no. We can do that sometime in between the lecture, not at the beginning of the lecture.
All right, Prof. All right. Please let me know when I should do it. Okay, thank you.
So what you're saying is you're not going to fix the marks and put them back to what they were?
I can't tell that yes or no. Okay. So this is the lecture. I got your question. So we will give some time later on to discuss this issue, okay?
All right.
We don't want to start the lecture with this kind of question at the beginning. You understand my point?
That's fine. So you're going to talk about it at the end of the lecture?
Sometime in the lecture, okay?
Oh, okay. Thank you, sir.
Okay, so today we have our lecture 7. So this is on flood frequency analysis. So you all know what is flood. Flood is a kind of unusual level of water rise in terms of water level and discharge velocity. And by frequency, we mean that how often they can come and at what magnitude. So by flood frequency analysis, we mean that we try to assess at a particular location that what kind of flood risk at that location. So this is very, very important to engineers because engineers, we develop housing, roads, a lot of infrastructure. And at many locations, there is a flood risk, particularly in the floodplain areas. Many of the cities, they are located in the floodplain or near the rivers. And there is a flood risk associated with that. So that's the flood risk assessment is a vital part in any development application. For example, if the New South Wales government decides that we release some land in a particular area for new development. For example, previously they released some land in Marsden Park, in Riverstone area, and also in many different areas of Sydney. So one of the first things they do the flood risk assessment that in this area, what is the risk of flooding? So in that kind of development application, this flood frequency analysis is very important. And there are many other applications. If you want to design an infrastructure like a bridge or culvert or a road, then you have to do the flood frequency analysis and flood risk assessment. So this class has a lot of practical application. So at the beginning, I'll discuss the basics of flood frequency analysis. Then I will discuss how we can compare various flood frequency analysis methods. By FFA, we mean the flood frequency analysis. For example, you learned number of distributions that can be used for flood frequency analysis. Can anybody tell that what are the distributions we have used so far in flood frequency analysis? Can anybody tell me what are the distributions we have used for flood frequency analysis so far?
Like quantile regression method, parameter regression method.
This are not right because they are not flood frequency analysis technique. They are regional flood frequency analysis technique, which we are coming at the end of the lecture.
Oh,
so by flood frequency analysis, we mean the at-site flood frequency analysis. We have used number of distributions before. We have used normal distribution because our tutorial class was that you have to find out the Q100 or Q50. That is the flood frequency analysis problem.
Yeah.
We have used normal distribution. What other distribution we have used?
Log normal.
Log normal, that's right. Any other?
LP3. Pearson type 3.
LP3, that's right. Any other? EV on, extreme value on or Gumbel distribution we have used, is that right?
Yes.
And we have used GEV, is that right?
Yes, GV, extreme value distribution, yes.
Generalized extreme value distribution, GEV, generalized extreme value distribution.
Yes.
So already we have discussed how we can use different probability distributions for flood frequency analysis. So then how we can compare, because we have seen that for the same site, if you use normal distribution or LP3 distribution or GEV distribution, for Q100 estimation, you will get different value. And sometimes they vary quite a lot. Sometimes they vary by 100%. Then how we can tell which one is the more appropriate for application in design? For that, we apply goodness of fit tests. So I'll discuss that to some extent. Then there are two special types of flood frequency analysis.
Sir.
Yes.
So, are you sharing your screen?
Oh, so I have not shared the screen to you?
Nah, we can't see nothing.
Okay, that's good that you have mentioned it.
Sir, where can we find the lecture notes?
Lecture notes are not available in the views, like in the views, should be in the views.
No, it's not there.
It's not there?
No, lecture 7 now. Or lecture, the next one, it's not.
Okay, okay. So thanks for mentioning that as well. Okay, so I'll put that immediately after the lecture. So, so let me share the screen first. So can you see it now?
Yes, sir.
Sir.
Yes, sir.
Okay, so these are the outline of the lecture that I was talking, the basics of flood frequency analysis, that I'll discuss that. I'll discuss how we can compare various flood frequency analysis methods by applying different goodness of fit tests. These are very useful, this goodness of fit test, and it is applicable in many other disciplines as well, many other subjects as well. Then we'll discuss at site flood frequency analysis. At site means that when we have a particular site, we have the recorded flood data available. So we know the historical flood data there, a different year, what was the highest water level there. We have that data for 20 years, 30 years, 40 years, 50 years, something like that. So at that location, we can use that data as we have done before, because I gave you some annual maximum flood data at different sites. And we have applied our program or Excel, how to use GV distribution or LP3 distribution to find Q100, for example. That is basically at site flood frequency analysis. But at many locations, we don't have the recorded data, flood data. And if we want to estimate design flood at that locations, then we have to apply RFFA, regional flood frequency analysis. That is a key term, RFFA, regional flood frequency analysis. I don't know what's happening. Okay. Under RFFA, we'll discuss the index flood method, probabilistic rational method, and quantile regression techniques, which are some of the popular RFFA technique. And finally, we'll discuss the ARR RFFE model, which is the currently recommended method in Australia for regional flood frequency estimation, RFFE model. That we'll discuss. I think at the beginning of the lecture, I showed that. And some students mentioned that why I am showing that at that time. I remember that. So this is the model that widely used in Australia. And this is the, I'll show you how to apply this model. And in the tutorial class, we'll show how to apply this model to do some regional flood frequency estimation. So firstly, let us discuss the basics of flood frequency analysis.
Sir?
Yes.
Does your screen change?
Sorry?
Does your screen change? We are on the same screen, sir.
You are not seeing the screen? Okay. Thank you for telling that. So maybe something happened. So let me do it again here. Yeah, something happened. Yeah, sorry about that. So you can see it now again, is that right?
Yes, sir.
Yes. Basic flood frequency analysis.
Okay. So these are some common things, just to give a little bit of perspective that why you want to do it. Flood is #1 natural disaster in terms of economic damage. If we consider all the natural disaster, then floods and storms, they are #1 in terms of economic damage. In Australia, average flood damage cost is $500 million a year. But in some year, this cost is too high. For example, in 2011, in that year, the flood cost was more than $20 billion in Australia. And around, I think around 38 people were died due to these flood events. So during 2005 and 2014, flood accounted for roughly 45% of all natural disasters and people affected by them, and cost an average of 6,000 deaths per year and $34 billion annual damage worldwide. You can see the magnitude of damage of flooding. That's why in most of the country, in terms of the development assessment, flood is regarded a big factor there. And flood experts are required in this kind of assessment. So according to UN Office for Disaster Risk Reduction, you can see the disaster statistics that really in some period of time that the floods and storms, and they are really covering the most of the disasters there, many of the disasters there. So we know that the flooding that happened in our Sydney in March 2021, that is not really only 6 months ago. So this is a kind of flood map that is for our Greater Sydney, because Greater Sydney flood risk is quite interesting, particularly in Western Sydney region, because the river system, we have the Hawkesbury-Nepean river system, which you can see in this map here. A lot of developments happens in this floodplain, particularly Penrith, Windsor, and lot of the new developments in the Riverstone, Marsden Park. They are under this floodplain. So it's a big issue here that how this development will be affected by flooding. And there is a lot of debate around it, that what sort of flood we should consider. Do we consider 100-year flood risk or probable maximum flood in terms of development assessment? So these are some of the photos of the flooding. I don't want to explain that too much, because it's all self-explanatory. Even the desert countries like Saudi Arabia, in this type of country, flood happens. And this is one of the flood events in Saudi Arabia that killed over 100 people, and that flooding in Saudi Arabia. More recently, there had been a big flood in Oman and adjacent country. And there was 100 millimeters of rainfall within a day, and that caused a lot of flooding in that country. Because the problem with this kind of country, like the desert country or arid region, is that people don't see the flood and they think it's not coming. But it may come sometime in their lifetime, and that can have a serious effect. Because many people, they do the development in the basement of the house. Because in the basement of the house in the desert area is good because it remains cool. But the problem is when the flood is coming, then basement gets flooded immediately, quickly, and then you don't get enough time to get out of the location, out of the flooding zone. That's why in this Saudi Arabian flood, a lot of people died in the jail because they were in the basement chamber and they died during the flooding. So flood has happened in the past, and it will happen in the future as well. And as engineers, we need to assess the flood risk using the best available technique, and then recommend and take necessary measures to keep the flood damage a minimum and to save the life of the people. So there are two key terms here. One is the design flood estimation and flood forecasting. So many people, they have confusion with these two words, which is obvious. But I'll try to explain, and I think you should remember it. So by design flood estimation, we mean that we are trying to find out some discharge value at a particular location for a particular risk or AEP, annual exceedance probability or return period, that will be used to design some engineering infrastructure. It may be a bridge, or it may be a dam, it may be a road, it may be a drainage system, it may be a flood embankment, and so on. So it is related to the design of some infrastructure. So that is the design flood estimation. Engineers use this a lot. What is flood forecasting is that it's a real-time, actual forecasting. For example, we all know that we will die, but really we don't know at what time we are going to die, generally, most of the time. If somebody can do that, really when somebody will die, that is kind of forecasting. Forecasting means that it is more precise, and really you have to tell at what time is going to happen. So in terms of flood forecasting, is something that engineers or scientists, they have to tell that at that particular location, say for example at Penrith, near M4 Bridge, say tomorrow, what would be the water level tomorrow at Penrith Bridge 4 at 9 a.m. in the morning. That is a flood forecasting job. So it is very, very important that it has to be quite accurate, because based on your decision, people will be asked to evacuate, for example. People may be asked to leave the place. That has a lot of issues, a lot of problems. And if your forecasting is wrong, then you're in trouble, really. You have to answer it that why it is wrong. So the knowledge that you learn in this chapter and the relevant lectures, it can be used in flood insurance studies. Because in Australia and developed country, there is flood insurance, but for many developing country, I think there is no such insurance probably. Because I'm coming from Bangladesh, and I know in Bangladesh probably there is no flood insurance concept that much. So by flood insurance, it means that if your house is damaged by flooding, the insurance company will pay for it to repair your house or rebuild the house if it is completely destroyed. So flood insurance companies, they have their flood assessment team. So maybe some of you might be working there. Flood damage assessment, this is needed when there is a big flood happening. Then you have to assess the damage to make the best planning, that how to reduce this damage in future and how to rectify this damage. And then the advice during flooding. So if some flood is going on, then you have to give advice that whether people need to evacuate or what precautions people should do. Then you have to plan for reducing the flood damage. For example, you may say, okay, we need to do the dredging of the river, or we may need to do some embankment, flood embankment along the river bank, or we may have to increase the capacity of the spillway. There are many, many other ways that we can reduce the flood damage. And flood risk assessment for development application, where many engineers, they work in this field last on, because every development that's happening, generally, you have to do a flood risk assessment. Particularly, I am telling about the big development, not the small house. If I want to build a house, of course, I cannot build my house. You know that in any area, like in many countries, that you can build a house wherever you like. But in developed country like Australia, if you have a farmhouse, you can build one house there, massive building, that's fine. But they will not allow you to subdivide that and make many houses there unless government has allowed that area for development. Otherwise, you cannot do it. So flood risk assessment is needed when you release the land for this kind of development. So I have given you a kind of brief knowledge that why we need to do flood frequency analysis and what is the usefulness of this topic. Now I'll come to the definition of the flood frequency analysis. So this is a kind of attempt to establish a relationship between flood magnitude Q and return period T, or AEP, annual exceedance probability. So you know that we did some flood frequency analysis and we made some plot. Is that the y-axis of Q and x-axis of return period T, or AEP, or ARI, something. So that is a flood frequency analysis. So in other words, its objective is really to estimate the design flood QT, where T is the return period. For example, what is Q100 at a particular location? So we already defined what is ARI, average recurrence interval, but here we are giving a more formal definition. So ARI, or return period, means that the average time elapsed between successive occurrences of a given flood discharge Q. So by 100-year flood, we mean that if we take 1,000 years, then this event will happen 1,000 divided by 100 is 10. 10 times it will happen. But in some year, it may happen 2 times. In some year, it may not happen. So why it's really average happening over a long period of time. So annual exceedance probability, AEP, you must know this term, AEP. After doing this subject, if you don't understand this page, then it's a problem. So AEP is equals 1 over ARI generally. There are some few other equations, but we can use this one. AEP equals 1 over T. But there is a problem when you use spot and annual maximum series. So then this kind of equation is not valid. You have to use different equation. So we know that there are 2 types of model we can use in flood frequency analysis. We discussed that at the beginning previously, that one is the annual maximum flood series, AM series. Another is the partial duration series, and I explained both of them by numerical examples previously. when I was going through the probability distributions. Can you recall that? Is that right? So for partial duration series, we introduced a distribution. What is that distribution? Can anybody tell me? For partial duration series, we introduced an equation or distribution. Can anybody recall that? So for partial duration series, generally two distributions are used. One is the exponential distribution. So for this one, two distributions are commonly used, exponential. Another is the GPA, generalized Pareto distribution. And for annual maximum series, there are many distributions we know, like normal, log normal, EV1, LP3, GV. These are different probability distributions we use. So in annual maximum series, we take the maximum value from each year to form our data series. And we assume that the data series have serial correlation 0. What is serial correlation? Who can explain to me? What is serial correlation? Is there anybody who can explain to me what is serial correlation? I think I explained that with a numerical example in some case, I guess. Probably I'll do that again today. Or if I have not done it before, I'll do it today. I will show what is serial correlation with a numerical example. So serial correlation is really how much correlation is there between the flood of this year and previous year. So this is called lag 1 serial correlation. And if I want to find out what is the correlation between the flood of this year and flood of the 2 years before, so that is lag 2 serial correlation. 3 years before is lag 3 serial correlation. So serial correlation is assumed to be 0 for AM series. And we know that for partial duration series or PDS, we consider all the events exceeding a particular threshold. And in this case, care is needed to ensure the independence of the data points selected from the same year. So it means that if you're selecting one event, then you should wait certain period of time so that you don't select another event, because the second event may be affected by the first event. So they are not independent of each other. So that's why, depending on the size of the catchment, you have to have a separation hour between your first event and the second event. So what are the assumptions in flood frequency analysis? This is very, very important for your exam, this part. What are the assumptions in flood frequency analysis? I may ask some question regarding this. I may give you some flood data, and then I can tell you that, can you tell whether this data satisfies the flood frequency assumptions? So one assumption is that data points are independent. So they are not correlated with each other, both temporally and spatially. Temporally means that is serial correlation. So that is serial correlation. So no serial correlation. And spatial correlation is particularly important for regional flood frequency analysis. the sample data is representative of the population. So we know the sample and population, is that right? So for a particular site, I have say 40 years of data, recorded annual maximum flood data. And it is available for me for flood frequency analysis, and I can fit a distribution to this data. Is this a population or a sample?
Sample.
Is it a population or a sample?
It is a sample.
Why is that? Can you explain?
40 years is like nowhere clear to nowhere near to the like for the population, which is like the data for very long time. 40 years is not long enough.
But what do we mean by population? Population means that we need to have the full data set. Is that right? Full population means that suppose I have 65 students in my class. So if I want to know my quiz 2 mark, quiz 1 mark, average mark, then if I have the mark for all the 62 students, then I can find the average value, and that is my population average.
That's
for
right.
some reason I have not got the data 40 students, but I select randomly say 20 students from that. And if I find my mean or average or standard deviation skew, that is my sample. Is that right?
Yeah, that's
this
right.
concept is to be very, very clear, the population and sample. Because you told that's good. I think you have told it correctly, but it is more than that, because at particular location, say I have 40 years of data, but that river have been created millions of years ago. And there had been rainfall millions of years ago, rainfall has been happening on that catchment and is producing flood or peak flow millions of years ago, since its creation basically. And we don't have that data. So our population is unknown. And the sample we have is so small as compared to the population. It's unbelievable in flood frequency analysis. Is it clear now? It's not clear, is that right? So can you hear me, students?
Yes, sir. We can hear.
Is it clear? So in flood frequency analysis, the sample we have is a very tiny sample of a huge population. Everybody agrees with that? If you don't understand this, then there will be a lot of problem, because then you will tell that the answer I have got from my analysis is correct. And I can use this design confidently. And you will design something and then the structure will fail. That's why you have to do uncertainty analysis, because your sample size is small and you never know the population. So that's why you have to do a lot of uncertainty analysis, because in many cases you have to estimate not 100-year flood, you have to estimate 10 million years return period flood. For designing Oragamba Reservoir, they have used PMF, probable maximum flood, and that has a ARI of 10 million years. So that means that we need 10 million years of data at least to estimate 10 million years return period flooding. But we may have data maximum 80 years or 100 years if we are lucky. So you are really dealing with a territory of uncertainty. That's why in this subject, the knowledge of statistics, knowledge of simulation, knowledge of programming is very important. But not at your level, but if you want to do higher study or become expert in this field, then that is the case. Okay, so I was talking about the assumption in flood frequency analysis. The population is homogeneous. That means that all the data points have occurred under same condition. So for example, I have a river which has a catchment is forested. And I have, say, 80 years of data there when the catchment was forested. And then there had been a lot of development in this catchment, like agricultural practice. There have been some cotton farm, or there have been some new township there. So that has removed some of the forest, and a lot of land use has changed. And then I have some data for another 30 years with the land use change data, and which is changing gradually. Every year, new development is happening on the catchment. Then say I have previously 8 years of data, and then I have another 40 years of data. So I have 120 years of data. So all of these data are not homogeneous, because for the first 8 years of data, it was under natural condition of the catchment. And the remaining 40 years of data under time-dependent development that is happening progressively on the catchment. So I cannot combine these two data sets to estimate my design flood in that catchment, because they are not homogeneous. Examples of non-homogeneity can occur due to land use change, as I explained to you. If you construct a big dam on the catchment, and also it can happen due to climate change, because climate change is increasing the rainfall intensity and the duration, because for 1 degree temperature rise, there will be 10% increased evaporation. So that means that our cloud will be loaded with more vapor and water. So when rainfall will happen, it will dump more rain in a short period of time, and that will increase the flood risk. So that's why due to climate change, you cannot use the flood frequency analysis the way we did before. So the flood frequency analysis that you have done before by using say GEV distribution, that is assuming that climate change is not happening. But now it is established that climate change is happening. That's why that kind of flood frequency analysis is not that much applicable. So you have to use non-stationary flood frequency analysis, which is a bit complex. And that is a bit of beyond the scope of this subject in this level. Like some of my PhD students are working on that. So it is basically a PhD level study. Because just I tell you why that is difficult, because we have seen that a distribution says the EV distribution has 3 parameters: location, scale, and shape. So we are estimating this location, scale, and shape with the data that we have. But due to climate change, these parameters will change with time. So that means that your location, scale parameter, shape parameter will change with time due to climate change. So you have to consider that change, how that will change with time. So they will be a function of time. Time dependent, time will be there in the equation, so that it becomes quite complex. And for that, we have to use non-stationary flood frequency analysis, which is a bit complex. So is there any question so far up to this level?
Excuse me, sir.
Yes.
Can we consider non-stationary flood frequency analysis as a time series? Because with the time, if the catchment pattern change and also the climate is changing.
Yeah, time will be there, but by time series modeling, what we mean by time series modeling is that we are using a time series of the data. So our annual maximum is the time series data. Because we're using each data point from 1 year. We can use our daily data, which is also a time series. So every time series analysis cannot deal with non-stationary. So you have to use a special time series analysis. Is that clear to you?
Yes, sir. I understand so far. Thank you, sir.
It's a quite complex territory, and you have to be a bit of expert if you want to do it. And you have very strong programming skills and understanding of the statistical knowledge. Any other question? Maybe I can ask some questions to the students. So can anybody give some example of the non-homogeneity of the flood data? I discussed few examples, but can you give some of this example or other example that what is non-homogeneity of the flood data? Are you listening to me, or you are everybody sleeping or doing something else?
No, as far as I understand, I can have a little bit discussion. Like if we have 40 years data, yes, like and the first 10 years are natural data, no interruption, anything by anything. And
no, you have to tell more. No interruption, no natural data. What natural data you are meaning, and what interruption you are talking about?
But if there is no dams or any other constructions.
That's right. Yeah, you have to be more specific. That's right. That's good. Yeah.
Yeah. So if we have some mixed data, like we have 10 years data, there is no constructions, and after 10 years there is some constructions, we have 5 years data, and then maybe there is another development or forest or vegetations. So if the data collection is changing over some human activities, so we cannot consider this type of data for that catchment as a homogeneous.
So there is non-homogeneous data because for the first 10 years is homogeneous, but for another 5 years under construction time, yeah, or agricultural practice change, that is within themselves, it is another group. So these two groups are not homogeneous. Is it clear to everybody? Okay, so why do we need to do the non-stationary flood frequency analysis? I want to hear the answer from some undergraduate student. Or I'll tell the name. Let me find the student list. Okay, Saika, do you have the student list with you?
Prof, yes, I have.
You have, okay. Anyway, probably I think most of the undergraduate students, they are sleeping or doing something else. So this is the reason why you get low marks in the exam. This is one of the responses. Okay. Okay, I think I will give 3 minutes break so that you can refresh a little bit. And then we'll go to the next part of the lecture, how we compare various flood frequency analysis methods. So 3 minutes break. Okay, I'm back. Saika. Dr. Saika, can you hear me?
Yes, Prof.
Probably I can, you can explain the maybe marking this time.
Yep.
So I'll stop share.
Sorry, sir.
Yes.
Can we go into a breakout room for 2 to 3 minutes, just because I'd like to ask a few questions about the exam in private. Thank you, sir.
No, I can't do that in breakout room now. You have to do a special session with me.
So because my issue isn't the result, my issue is I received the result on views as like 46 out of 50. And then now if you log on to views and check, it's dropped down to 41 and there's no explanation, feedback, nothing. And I don't want general feedback because general feedback doesn't apply to me. I'd like
that's
to know
fine. I can
feedback.
appreciate that, but not at this moment because I cannot keep all other students waiting for you. So you can have a special session with me after the lecture.
After the lecture? So after this lecture, we can talk? Yeah. So after this lecture, we can do whatever we want.
Yeah, after the lecture, I can do because I have 1 year break and then I have another tutorial class.
Okay, so after the lecture, we'll talk, sir.
Okay, immediately after the lecture, I'll give you another Zoom ID.
All right.
And then I can
Thank you very much, sir.
What's your name?
Right, thank you very much.
What's your name?
Salah Dawit, sir.
Okay, that's good.
Thank you very much, sir.
Welcome. Okay, so Saika, can you share your screen?
Yep, Prof. I can share.
Okay.
Can everybody see the screen?
Yes.
Yes, we can.
Yep. Then here, I'm just showing you the solution for question A and B. Then first question was that about the histogram. You have to just make a comment on the histogram and then you have to make the probability of over 50 millimeter rain. And you can see here, just I made a rainfall histogram and the comment will be that the histogram is right skewed because the mean is greater than median here. And the probability would be the cumulative frequency divided by number of event. Frequency divided by cumulative frequency into 100. It will be 16.67%. This is for question A. And for B, we have to estimate the CV value. Most of you guys just express the CV value in percentage, and some of you express it in the this fraction way. It's all right, but fraction way is, Prof was telling me that fraction is greater than percentage because CV is expressed in that way by fraction. And here you have to make a comment on the CV value to compare with the humid region. And for humid region, we know that the CV value must be below than that fraction because the CV value of the humid region will be smaller than the Australian values because Australia has a high variable hydrology as compared to humid region. Now I'm going to question C. Here you are supposed to estimate the Q50 from 2% AEP. And here the return period will be 50. Some of you guys just made the same mistake as before. You didn't calculate the T values properly. So just become wrong. And the F value will be 0.98. And from we have to do the interpolation. The interpolated value will be 2.054. If I keep the here, if you see the difference here, the equation of difference, sorry. Yep. By using the equation, we just calculated the difference and then we just got that value. And the result will be that one. But some of you just made a mistake in the interpolation, so that result got varied. For the second part, you have to calculate it by using the Excel. That is the norm ion weight equation here. And the result will be that one. And for the R, the result will be very close to that two values to answer. This is number C, the 3 parts of C. And for number D, we have to just transform the values, rainfall values into log distribution first, because we were supposed to do the LP3 distribution here. So this is the log normal distribution, log 10 distribution. Here we got the mean from the log 10 values and the standard deviation. Then we got the skewness here. From that skewness value, we did the interpolation here. And some of the students just you did a mistake in counting reading the SQ value here. Here we got 1.12. So we have to choose two numbers. One is below 1.12 and one is above, slightly above 1.12. Just near to that value, the lower values and the upper value. So you made some of the students have made mistake here in reading the SQ values from the table. So here we got the interpolated value 1.42343, and we just got that value from that equation, mean plus standard deviation into K2. And then we just again transform that log 10 values to normal values. And the number will be 168.6 meter cube per second. And for you have another question to reviewing on paper for Tasmanian flood frequency, for estimating the, let's go to the article. Selection of the best fit flood frequency distribution and parameter estimation procedure for Tasmania. Here, some students just well explained the review article, but most of the students didn't get the point what should present in the review answer. Mainly, we have to focus that the article have selected 7 different probability distribution for Tasmania. And from the 7 distribution, they found that 2 parameter distribution are preferable over 3 parameters one for Tasmania. And for log normal appears to be the best selection. And the paper also just identified that for parameter distribution, the Bayer procedure provides the best parameter estimates for log normal distribution over the other parameter estimation procedure. And these findings is important in that sense that usually 3 parameter distributions are preferable over 2 parameter distribution for Australia. But in Tasmania, it is different from Australia. There the findings is 2 parameter distribution. So these results doesn't just suit for estimating the flood frequency distribution in flood probability distribution for Australia. So some of you guys just got the right answer and some of you are not. So please be careful about the reviewing of an article. You have to always focus on the abstract and the conclusion and the results part for reviewing an article and the methods also. So that's all. Thank you. If you have any question, please proceed. Do you have any question so far about this solution?
Excuse me, ma'am.
Yeah,
I had a question that why did the marks change? Like, why did you give 1 marks initially and how did it change after some time?
But how did you see the marks when it is finally published? Because sometimes just we just got the wrong concept and then I just again corrected it, but it was not finalized at that time. You got the access on the views before
but
finalizing?
a lot of people had that issue where we all received our marks, and then now they're all changed for everybody. So
but how did you got the marks before
you guys posted them on views? How did we say you posted them on views? It's not our fault. You guys posted them on views.
Okay. Then I have to explain you that initially our results are something different from the these on final on. So you have to made it again correctly. And this is the actual results now you got.
Can I say something here? Can I say something here?
Yes, sir.
Like the views is such that whenever we put something, then mark is there. Sometimes we do partial marking. Like we don't do all the questions at the same time sometimes. So the mark you see sometimes, that is not the final mark until and unless we have finished all the marking, and sometimes I review the marking as well. And sometimes I increase the mark and reduce the mark as well.
Sorry, sir. But how are we supposed to know? For on views, for us students, all we see is quiz and then mark. We don't know partial marking, full marking.
So you have to wait.
Whether you're editing it.
That's why you need to wait, and so you have to wait in the some time basically.
So, but it's not really our fault though, because if you guys posted the mark,
it's not your fault.
Every other teacher posts the mark, and that's our final mark. So the basic assumption is we get our mark. That's our final mark. So that's why all of us are.
But why you are so angry that your mark is reduced?
Because we don't have any proper feedback. We have general feedback, no individual feedback to show why.
Yeah, of course we give the feedback. First, we have to give the general feedback. Like we have now showed you the answer of each of the question. Is that right?
Yes, sir.
So now you know where you have done mistake. Is that right?
No, sir. I want individual feedback.
Okay, of course, individual feedback will be given. Of course.
Right.
And during the individual feedback, I can reduce the mark as well. I have that right. Because I have not done the marking and I'm the unit coordinator. And if I am looking at some marking and I find that it has been overmarked, I have the right to reduce it. And I do that as well.
So then when do we have a final mark? Since anytime you guys want, you can go in and edit our marks. When do we actually get a final mark? You can't just play around with us.
Once the result is out in the after class, like today we are discussing the mark, and you can assume the mark what is in the views. That is the final. But still I can reduce some of the mark as well.
So my question is, when will marks not change? So when are they final? Because normally for us students, the second that goes on views, that's the final mark.
Mark is final when you will get the final mark of the exam at the end of the semester.
So from now to the end of semester, if you decide to go back to quiz 1 and remark it, we can lose marks.
I can do it. Yeah.
So that's unfair.
Yeah, it's not unfair because we can adjust the mark anytime. We can scale the mark anytime. And most of the time we do the scaling for the favoring of the student. We don't reduce the mark, but we try to increase the mark.
All right, so we'll talk after then. Thank you. We'll talk at the end in the Zoom meeting. Thank you.
Okay, is there any other question?
Pay attention to so how can we get our marks, sir? Like me?
So don't like every time we'll post the mark in the views. We'll tell particularly that happens in the class. We review the mark in the class and we disclose it. And that is the kind of final mark, of course. But if there is a mistake in the marking, of course, the student has the right to ask for the review, and I will do the review, of course. But in the review, marks may increase or decrease because when I see there is some mistakes in the marking, and if it is to my knowledge, then I have to reduce the mark. And if I see some reduced mark, I have to increase the mark. That I do all the time. And then you need to place a piece of paper.
Actually going to complete the writings. Now it sounds easy. Can I get what your point? Can you got my point, sir?
I think for master's student, I have not done the marking as yet. For the PhD student. I should do that. I'll do it.
Okay, sir.
Sir, can you
is
please
there any other
mute
general question about the mark? Saika,
Sir,
can you show the distribution of marks?
Sorry, sir. Can you mute the student that has their mic open? Because it's very distracting.
Here is the mark distribution based on the grading system. 16 students just got below 50 out of 100. That is the percentage mark. 5 students got below 65, 6 students got below 74, 8 students below 84, and 5 students is over 85 to 100.
So in other words, Saika, in other words, we can say that 5 students got high distinction.
High distinction.
And then 8 students got distinction, 6 students got credit.
Yep.
And 5 students passed, and then 16 students failed. Is that right?
Yep.
So 16 students failed. So that's a it's a great number of students failed here.
What will be the grade between 65 to 74?
Credit, just put a C for credit.
And
then P for pass. And F for fail.
Okay.
A distinction for D and HD.
Okay.
Anushya, can you please mute yourself? If you are not asking any question, can you mute everybody? If you are not asking a question, when you are asking a question, you can unmute at that time. Otherwise, all students should mute. Is there any other question on the marking? Okay, if not, then Saika, can you stop your sharing of the screen?
Yeah, Prof. Thank you.
Okay, now I'll discuss how we compare different flood frequency analysis methods. So we know CDFs and PDFs. What is CDF? Who can tell me what is CDF?
Cumulative distribution functions.
And what is PDF?
Probability distribution functions.
So these are the two different things. In flood frequency analysis, we generally compare the CDFs instead of PDFs. So we plot the CDF on a log normal probability paper. And then we can see how well the data fits the fitted distribution. I'll give you some example later on. Then we can use some formal hypothesis testing using chi-square test, for example, or Kolmogorov-Smirnov test, or Anderson-Darling test. There are other tests as well to assess or to evaluate the hypothesis that whether a particular distribution fits the data or not. But the problem with this hypothesis test is that they are quite generous, and they try to accept that most of the distributions are okay. And most of the professional people, they really use a kind of professional judgment that they compare the fitted distributions with the data points, and they say whether it's good or bad or very bad fit. Sometimes they include third and fourth moments in the assessment. By third moment, we mean the skewness, and fourth moment, we mean the kurtosis, for example. So we can use those to do some kind of hypothesis testing. But with the short period of data, this estimation of the third and fourth moment is quite low accuracy. So this is an example that what we mean by this kind of statement that I made before, that in the x-axis, we have the return period or AEP, and y-axis, we have the discharge meter cube per second. And we see that the smaller triangle here, they are the observed flood data. We can plot these by using, I show you on class that how we can plot the data by computing the ARI, and then we can plot the data in Excel. And then this is the fitted distribution. In this case, it's LP3 distribution. So this expected parameter quantile is this line. And then we have expected probability quantile. They are very similar generally. And then you have the confidence limit, that you learn the confidence limit, how to build the confidence limit, 90% or 95% confidence limit. This is 90% limit here. So that means that according to the fitting of the probability distribution, LP3 distribution, say for 100-year flood, your estimation is coming as this value here, for example. But you see your uncertainty is starting from here to there. Then the question will be coming that in the design, which value you want to use. And it's a big difference because this is 1000 meter cube per second and this is 2000, this is 3000, this is 4000 meter cube per second. So this is here 4000 meter cube per second. And here we have around 200 meter cube per second. And our expected value is here, which is 200 here, 300, 400, 500, 600, 700, around 700. So you can see that your result that you are doing, that will give you 700 meter cube per second, but the confidence limit, 90% confidence limit is 200 meter cube per second to 4000 meter cube per second. Then you have to make a decision that what would be the design flow. Is it 700 or 4000 or something in between, or what you want to use in design? Similarly, this is another example that we have the fitted distribution here, and then we have the confidence limit. But if we want to assess it, that is this fit good or bad, what do you think? Without doing any testing. This is our observed data, and this is my fitted distribution here in the middle line. So does the fitted line messes with the observed data very well?
It seems to me it is better than the earlier one.
So you think this is probably in the rank of, is it good or very good? How do you think?
I think it's good.
And in this case, you say it is probably fair.
Yeah, I think so.
You're right in the sense, because you can see here that the number of data points are not that many here. And you see here in the lower is a problem, and in the higher it's a kind of problem there as well. But one thing you have to keep in mind, that the higher flow has a lot of uncertainty in the measurement because it is coming from a rating curve. It is not coming from the measured data. So in the lower level here, these data are more accurate. And the higher points, they are quite inaccurate. Sometimes there might be 40, 50, 80% error with those points. So that makes the problem more difficult. So we can really assess this kind of goodness of fit test. There's another technique is called probability plot correlation coefficient method. That is probably better than many other techniques. Then we have the L moments based test. So far we have used our normal mean, and we have used standard deviation and skew. These are called ordinary moments. But L moments are different ordinary moments. So L moments are better because they are less affected by the outlier in the data and sampling variability of the data. The L moments are superior than ordinary moments. So, but in this lecture, we are not introducing the L moments because it's not easy to compute. L moments, the flight software in Australian rainfall runoff, it uses L moments. And another way that we can plot the data on the 2-parameter distribution on the log normal paper, but this cannot be done for gamma and LP3 distribution. I think we have discussed this paper that I think it was in your exam, and also discussed this in the lecture note, in the lecture as well, that they compared different distributions and fitting for a particular state of Australia. So to do the at-site flood frequency analysis, we have to follow in Australia the Australian rainfall and runoff. So I think you all downloaded the Australian rainfall runoff, is that right? Have you downloaded the Australian rainfall runoff in your computer?
Yes, sir.
I think we showed how to do it at the beginning. So the Australian rainfall runoff, you have book 3, chapter 2, and chapter 3 that you have to follow in your practical career. If you want to do flood frequency analysis, then that is the guideline that you have to follow in practice, in practical application. This is the kind of code you can say. So this chapter is at-site flood frequency analysis, chapter 2, written by Professor Jascouz and Stuart France. They are from University of Newcastle. So this is the book here. That the first page I have shown here. That really this you should read this chapter. It is available to you, freely available, and you should read this chapter. And they have recommended. They have not recommended any particular distribution for flood frequency analysis for Australia. In this ARR, we call it ARR 2019. In this ARR, they have not recommended any particular distribution, but they have given examples of 5 distributions which are log normal, and then EV on, then LP3, GV, and GPA. So they have given example that log normal, EV on, LP3, GV, and GPA, generalized Pareto distribution, can be used, or people should consider this, and then they have to make a decision. So they have not specified the distribution, but in the previous version of Australian rainfall runoff ARR 1987, they recommended LP3 distribution for use in Australia. Currently in US, they recommended LP3 for use in US, for example. LP3 distribution is recommended by many countries, but Australia this time they said no, we cannot recommend a distribution, because in case of Australia, we have found that LP3 is not very good for many sites. Then the problem is, if you specify LP3, then the authors of the ARR, they're taking the responsibility that if there is a mistake or something happened, then people may sue them, because they have recommended it. So people may sue the Engineers Australia, who is the publisher of this ARR. and the individual authors as well, maybe. So that's why they said, no, we don't want to recommend any particular distribution, but these are the distribution you can try, but we don't really give you a specification that you must use this one. You have to make a decision. So any question on at-site flat frequency analysis? So you should read this chapter, and that is the homework for your next week, that you should read this chapter and the following chapter as well. And then we'll discuss in the next week these 2 chapters, because this is very, very important.
Just a quick question, sir.
Yeah.
So is there any threshold or assumptions like how many record length for the at-site flat frequency method? I mean, what are the length of the record? That's a very good question.
That's a very good question. Yeah, that's a very good question. So there is no specified guideline like that, but the expert people, they use something that we have to use 2T length. So if I am estimating 50-year flood, then I need 100 years of data. If I want to estimate Q100, then I need 200 years of data. That is the general rule. Did that answer your question?
Yeah, yes, sir. I got my point.
It is very, very important to know this. But really, it's a kind of guideline. You will not find this kind of things in the book, because you really cannot claim that is the case, but it's a general kind of thumb rule. But in Australia, our data length is so small that we cannot apply this rule, because in New South Wales, we have maybe hardly any station having more than 100 years of data. So how we estimate the 100-year flow? We need 200 years of data. That's a lot of uncertainty. That's why you see the confidence limit is increasing so much when you are going to higher level ARI. You see here, when you are going to higher level, then you can see what is the uncertainty. Is that right? Because you have only, say, 20 or 30 years of 30 data points, and we are using that for estimation. So here you see we have more data points. That's why our confidence limit is a bit like tight. But previously, our confidence limit is quite wider, more uncertainty.
Can I, sir, can I add one comment from a basic understanding? From a basic understanding,
please.
Like if we are using only 50 years record data, so if we are like to go for 100 years prediction data, so in that case the uncertainty might be higher because we are getting more extrapolation there. Does it make sense, sir?
Yeah, of course, extrapolation, of course, you are doing extrapolation because you want to estimate 100-year data and you have 50 years points of data. So you are doing extrapolation of the probability curve. And at the same time, when your sample length is small, then your estimation of the mean standard deviation is with more uncertainty there. So that is increasing your confidence limit.
Sir?
Yes.
Sir, in this graph, from this graph, if I need to pick like in a professional area, if I need to pick a number for 100 years flood as a design flood, what number should I, like as a good designer, what number should I consider?
I think that's a very good question. As a designer, you have to make a decision. And generally, a guide is that if it is very important structure, particularly in the city area, very important structure on a busy road or something, you are designing a bridge, then you should go to the upper level. But that will increase the cost because you can see here that the expected value or the most probable value is around 100 meter cube per second here. Is that right?
Yes. Yes.
And your upper value, upper limit value is 250.
Yep.
So it's really, it's around more than double, is that right?
Yes.
So if you increase your size of the structure by double, then your cost will increase by 3 times generally.
Yeah.
So it's this issue of budget and economic analysis really what you want to use. So if the failure of the bridge causes a lot of problems, a lot of economic issues, then you should consider the higher level, like higher upper limit. You know, when we do the structural design as an engineer, we use factor of safety, you know?
Yep.
Like when you design a beam or a column or something,
yep,
you use the factor of safety, sometimes 1.52.
Yes.
This is kind of factor of safety that really what you want to use in your real design that depends on the importance of the structure.
Okay, sir, in the reality now, if we consider like our Western Sydney backyard, the Peak Town area, there is lots of development is going on. If we are considering new development there, and we are also considering flood, we are doing flood analysis for that area, like we're making channel, open channel, and we are considering flood thing. So in that case, what will be the like a good judgment to
I think that's
consider?
a very valid question. That's a very good question. Since you're working in the industry, you're asking this kind of question, which is important. Because the issue is when you do some urban development, say I'm living in the Plumpton suburb, and we have some breeze in this suburb, and then there is some breeze in the M7 freeway, which is also going through Plumpton. Okay.
Yep.
So when I am designing the breeze on the M7 freeway, I must consider very high, like the factor of safety.
Yep.
Because if that breeze fails, then it will a lot of consequence. But if a breeze is failing or something flooding happening in my suburb, then its economic consequence is low as compared to that one. Okay.
Yeah.
Because the problem is, if you want to make all this breeze very high safety factor of safety, then the cost will be very high, and basically all the cost will be passed to the people who are buying the land in that area. You know that.
Yes.
Because
true.
Nowadays your raw land price is $100,000, say 400 square meter land. Raw land is say $150,000 in Riverstone, in that kind of new area. Raw land. I am meaning raw land without development. And the developed land is $600,000 or $700,000 for 450 square meter land. Because all the development cost of the road and breeze and everything has been passed to you, who is buying the land, you know. So that's why you cannot go for a very high factor of safety unless the kings or lords, they are living in that area, they are very rich and they want a very high factor of safety. But in the design, generally in the suburb, we use very low ARI for design of the drainage infrastructure. 20 years, maximum 50 years, 100 years, this kind of things.
Yep, true, sir. Yep.
Because otherwise it will be too expensive.
Thank you, sir.
Welcome. Okay, then I go to finally the regional flood frequency analysis, RFFA. So this is needed when you don't have recorded flood data at the site, then it's really bad. Previously, we have seen that we have data, but in many cases, very short data as well. So in that case, we can use the RFFA as well when you have data length short or no data at all. So it is used for unguessed catchments, and that is the case in many applications. This involves transfer of flood information from guessed to unguessed catchments. And the concept of homogeneous region is very, very important here. And Ali Ahmad is doing his PhD on this homogeneous region. Is that right, Ali Ahmad?
Yes, sir, of course. Yeah.
So Ali Ahmad will be doing his 4 years study on this topic. This 2-word homogeneous region. So he'll spend his 4 years on this topic to get a PhD. So this is a very, like by homogeneous region, we mean that here, that the catchments in my group, they are similar to each other. So by that we mean the homogeneous region. But how to measure the similarity, it's not easy, it's quite complex. So when we form the regions in the flood frequency analysis, by region we mean that, okay, we may say, okay, our Blacktown Council and Penrith Council, there is a homogeneous region and all the catchments in this area, they are homogeneous. So we can use the flood data recorded in this area to estimate flood data, estimation at other location where we don't have data. So I'm assuming that my Blacktown and Penrith and say maybe some other parameter council, they are homogeneous. And to make that a statement, you have to do a lot of analysis and a lot of things. So in forming the regions, one can be done in the geographical space. Another can be done on the catchment attributes space. So by geographic space, we mean that we are assuming that, okay, all the catchments in Blacktown Council or in the New South Wales state, they are homogeneous. Or you may say that, okay, in New South Wales, I have two guest catchments where I have very good data. And then I will say, okay, let me divide the catchments, those who are very, very small catchments, in one group. So that is my homogeneous region on. In another homogeneous region, I may say, okay, let us take all the catchments which are very small, but highly forested, or they have very high slope, or they have very high mean annual rainfall, or so on. But the problem is the flood response depends on number of characteristics. It is not only one characteristic, but it depends on the size of the catchment, slope of the catchments, then forest of the catchment, then soil characteristics of the catchment, shape of the catchments, and so on and so on. So that means that it's become complex because it's a multi-dimensional problem. It's not a one-dimensional problem. So that's why we may have region on our catchment attribute space, which is more complex, but there are techniques of doing it. And then under this fixed region, we can have fixed region based on geophysical boundary. Like we may say that all the catchments in the west of the Great Dividing Range, they are homogeneous. And all the catchments in the eastern side of the Great Dividing Range in New South Wales, they are homogeneous. Or we may say that all the catchments in New South Wales state, they are homogeneous. Or all the catchments in Victoria, they are homogeneous. In ARR 1987, they used this one to form the region. And in the case of catchment attribute space, you can use cluster analysis that I will discuss that in another lecture. This is a technique to divide the data into homogeneous groups, a statistical technique. And we have the ROI as well, which is region of influence. Region of influence, ROI. I have noted it here. So ROI is really advanced that it tells that there is no fixed region as such. Rather, for every catchment, you need to define your own region, either in the geographical space or in the catchment attributes space. So this is the most advanced approach. And in our Australian rainfall runoff, this ROI has been recommended to apply. Any question on this? It is highly relevant to some of the PhD students as well, particularly for Ali Ahmed. Ali Ahmed, do you have any question?
I think it's okay for me.
So there are many different RFFA techniques. One of the common is the index cloud method, probabilistic rational method that was recommended in ARR 87. And then there is quantization technique as well. So I think in the last lecture, I showed you quantization technique, is that right, in SPSS? So in the last lecture, in the last tutorial class, I think I showed you the regression technique, is that right?
Yes, sir.
So we have explained that in the by SPSS software. And PRM, probably we'll do that in tutorial class. And then we have index cloud method as well. So these are the different techniques you can apply. So probabilistic rational method was recommended in 1987 in Australia. And that was used till 2016. Although ARR came in 2019, but an interim version of ARR arrived in 2016, particularly for this RFFA technique. So people started applying this 2016, and from 2019, this method has been what I would say, not recommended in Australian program. But still people are using it because they want to compare what you get with the new RFFA technique and this old one. So this method is very simple to apply, that QT, Q100, You can estimate it by knowing the area of your catchment and the rainfall intensity on your catchment that has a duration of TC. TC is a function of area of the catchment. And this T is the return period of your flood that you want to estimate. So how to estimate this ITCT? Australian Bureau of Meteorology has a tool, IFD tool, that in any location in Australia, you can estimate this ITCT. And A is the area of the catchment. You can find that on a topographic map. And then you need another coefficient, CT. That is the runoff coefficient. So for runoff coefficient, there are some prediction equations available, or there are some maps available that you can use to estimate the runoff coefficient by interpolation. It's easy to apply. It has only two predictor variable, catchment area and resultant rainfall intensity. And CT is really considers all the factors of all other characteristics in CT. Limitation is that the estimation of CY or CT, same thing, is very, it's a lot of error in it, but nobody knows how much error is that because there is no independent testing of it. And we don't know what is the estimation error, so we cannot develop our confidence limit of the estimation. That is the biggest problem with this PRM. In case of quantile regression technique or QRT, we develop a kind of equation like this, that QT equals a function of characteristics like your B, C, D. These are the catchment characteristics. They are catchment area, rainfall intensity, and so on. And these regression coefficients, A, B, C, they will be estimated by methods such as ordinary least squares and GLS, generalized least square. So last time when I showed you how to estimate the coefficient of this equation last tutorial class, then we used OLS, ordinary least. It is easy to apply, but GLS is really difficult to apply, and it is more sophisticated and more advanced. And in ARR or rainfall runoff, this GLS technique has been applied. So QRT method generally gives this kind of equation. Like we developed this kind of equation in one of our papers, but this is not recommended for use, but we developed this kind of equation for New South Wales. In this paper, we compared the PRM and QRT method. And we published a paper in Australian Journal of Water Resources in 2011. So if you want to know more about these two techniques and how they compare, then you should read this paper, particularly those who are doing PhD or thesis, undergraduate or master's thesis in this area. They must read this paper. In this paper, we compared the fixed region and ROI, region of influence approach, by my former PhD student Khaled Haddad and myself. And this is one of the key paper in regional flood frequency area published in Journal of Hydrology. This is one of the most cited and important paper. And this technique has been now adopted in Canada and some other countries as well, based on this paper. So this RFFA technique was developed in our university, in Western Sydney University. It started in 2003 and it went up to 2016. So we did a lot of research and we are the big project team. I was nominated as the project leader. And then some of my PhD students like Dr. Khaled Haddad, Dr. Mahamood, they helped me in this project. And also Professor Josh Kuzera from University of Newcastle, Erwin Weinman from Monash University, Ashish Sharma from UNSW, they were part of the project team. many other people as well. So in this ARR, like this chapter 3, we have recommended based on GLS regression to regionalize LP3 distribution with region of influence approach. So this is one of the most advanced RFFA technique in the world because we have applied very sophisticated and like the cutting edge technology at the like the high, upper end technology in this technique. This is being now adopted in many other countries. They are trying to upgrade their method following our approach as well. And we developed a software, and you'll be using that software in practical class, in tutorial class. And all of these things is implemented within this software. So the program was mainly initially written by Khaled Haddad, but final program, I wrote the program in 4 languages, and then that is has a window interface. And it does a lot of calculation, Monte Carlo simulation within seconds. So this is available in this project. It was called Project 5. ARR revision has 20 projects. So this was project 5. So you can download this chapter, and I think you have downloaded already the ARR, and in that book 3, chapter 3, the regional flood methods. And this is the book in the ARR. That is the regional flood method, chapter 3, peak flow estimation. And it is, I was the first author of this. So this is the group of the authors. And I regard this is the best research outcome in my research career because this is being used like in the last 5 years, it has been used more than 10,000 times, the software and the chapters. So it is widely used in the industry, and it's highly developed, and really it's a teamwork, like all the people, all 4 of us, and also other people as well. So the software looks like this. If you click on the software, it's very user-friendly, free to everybody. So anybody can use it. So because when they gave us the money, we got around $600,000 to develop this software. So Australian government, they gave us this money, and the condition of that, it has to be free for everybody. So in this software, you will see that you will see a screen like that. Then you have to name of your unguessed catchment, and then you have to give the latitude and longitude of the catchment outlet, which is like if you have a catchment like this, then this is called the outlet, and say, so this is like the river, and then this is might be centroid here. So really you need to know the latitude and longitude of the centroid and the latitude and longitude of this, and you put it here. And then you measure the area of this catchment, how big is your catchment, then you put it here. And then you click on submit. And within a fraction of a second, you will get an answer with your flat quantile estimation that will show during the tutorial class. So the highlights of this technique is that this has been included in the 4th edition of ARR. We used 853 guest catchments over Australia to develop this technique. That included 798 guest catchments and 55 catchments from arid region and 798 from the humid region, coastal area. It allows estimation of design flood from 50% to 1% or 2-year to 100-year return period, small to medium-sized catchments. And Australia has been divided into a number of regions, number of areas to apply this technique. So basically, as I mentioned before, that it has applied it has generalized the LP3 distribution using a Bayesian generalized least square regression framework. So in summary, we have discussed basics of flood frequency analysis. I explained why we need to do flood frequency analysis and what are the possible applications. What are the assumptions of flood frequency analysis? And we discussed how we can compare various flood frequency analysis methods, or we can do some goodness of fit test, although I have not showed you how to carry out those tests. but these are available in the software that can be done. I have discussed the at-site flood frequency analysis and regional flood frequency analysis both briefly. We have discussed the PRM, and I have explained a little bit QRT and ARR, RFPP model as well. So in fact, this is my area of expertise. Regional flood frequency analysis is my area of expertise. Basically, like I do research in a number of fields, like you can say 4 or 5 areas, but this is only my number 1 area, regional flood frequency analysis. And you can reckon me as a kind of expert in this field, that RFFA, not in Australia, but globally. So do you have any question?
Sir, just one quick question. Yeah. As we can see that there are 798 humid catchment in Australia, and where only 55 catchments are arid. Yeah. So there are total 853 catchments that we have considered for ARR modeling. Yeah. So if someone would like to do something comparison between these two catchments, like arid or humid, so what would be the methods or criteria to select the catchments? Would it be proportionately or something else?
In the arid region means the central Australia, like the Australian periphery is generally humid. About 75% of the interior of Australia, they are humid, like the arid and semi-arid. And the rainfall is less than 300 millimeters per year on average. So this is called the arid and semi-arid region. But the problem with the arid and semi-arid region is that we don't have that many guest catchments, because not many people live in those areas. So, and not that many developments happen in those areas. So we don't have data. That's why we could find only 55 catchments, hardly from this vast area. So that's why the approach we have developed is not very accurate for arid and semi-arid region. And if somebody wants to compare the two regions, then there are a lot of uncertainty for the arid region, because there is not enough data or information to us. So that's why it is very low accuracy as compared to the humid region where we have 798 guest catchments. So that is the kind of answer, but it's due to practical limitation, because we don't have data. If you don't have data, then you cannot do anything.
So as we know, to be a representative sample of some population, there should be some criteria, like from 55 catchments, I should say something like 20 catchments. Or like,
you're right. I think you're right. Like when we have 853 guest catchments in our humid region, then when we are doing ROI, region of influence approach, say at particular location, say you are in Penrith, Kingswood area in your university campus, and I want to design a structure there, breeze in a creek, and I don't have any data. So I have to select some catchment. I have to define my ROI. So I may say, okay, all the catchments within 50 kilometers of this location, I select them. So we did a lot of optimization simulation. In fact, we have published more than 60 articles on this issue. And many of them, they are in high quality journals. And there have been 7 PhD students who completed their PhD under this project. And many honors students as well. Some of them, they got first class honors, and many of the students, they are working in a very high level company nowadays from this project. So the issue is really, we found that you need at least 20 catchments to estimate your mean value of the LP3 distribution. And you need at least 30 catchments to estimate the standard deviation of your data. And you need at least 60 catchments, 50 to 60 catchments to estimate your skewness of the data, because as the moment increases, your uncertainty increases and you need more data to estimate it. So for example, if you want to estimate kurtosis, you may need 100 catchments data. So that's why we have our expanding region. So we don't fix our ROI. So our ROI depends on the parameter you are estimating. For mean, we can say, okay, if you have 20 catchments around your site, is fine. But when you want to estimate a skewness, we say, no, it's not good enough. You need to have 60 catchments or 100 catchments to estimate your skewness. Is it clear?
Yeah. I think it depends on my parameter, which is my own.
Because if you want to estimate higher order moments, you need more data, because to estimate higher order moment is very difficult, and you need very long data because you are dealing with sample. You need a bigger sample size.
Yeah.
Otherwise, your estimation will be rubbish.
Yeah, I got your point.
Any other question by any other student?
Hey, sir.
Yeah.
Just quickly, are you marking attendance?
Yeah, we should. Saika, can you do the attendance now? Is Saika here?
Attendance? Yep, I can take that.
Yeah, because we have 10 minutes left, which is good.
Yeah.
We have finished within time because it was a quite big lecture. So next week, I want that you read these 2 chapters. That is the book 2 and 3, chapter 2 and 3 of book 3 of ARR. And I'll ask some questions. So next lecture, first around half an hour will be the question. If you don't understand anything from these 2 chapters, then note it down. Then I will answer those questions to you because I think that is a good opportunity for you to understand these chapters, because it's not easy to understand. When you read, you will realize that, because it's written for the professional people and it's very advanced technique. So you must note at least 2 questions by each student. And then we'll discuss those questions in the first part of the next lecture.
Prof.
So Saika, you can do the attendance now.
Prof, can you hear me?
I can.
Oh, yeah. Thank you.
You can do the attendance now.
Okay. Okay, good afternoon, everybody. Please be attentive for attendance. Al-Hamidi?
Yeah, I'm here, miss.
Thank you. Al-Saifi? 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 Lloyd? Lloyd, Ahmed Sharmad Aloyd? Al-Jahraini?
Yes, I'm here.
Thank you. Amuttu Srishtha?
Yes, I'm here.
Thank you. Asifullah?
Present.
Thank you. Then Beud? Nan Sharma Yusuf Beud?
Yep, present.
Thank you. And Alexander Baker? Baker?
Present.
Thank you. Bastian? Bastian? Kapak Bastian? Kapak Bastian? Alex Brook? Alex Brook?
Yeah, here, miss.
Thank you. Kalim Koim? Kalim Koim, John Kalim Koim?
Yep, here.
Thank you. James Carpenter?
Me, miss.
Thank you. Salah Darwish?
Yeah.
Thank you. Tiki Desha?
Here.
Thank you. Dungana, Nauruz Dungana?
Yes, miss.
Thank you. Suleiman Faisal? Suleiman Faisal? Oliver Frame?
Yeah, I'm here.
Thank you. Then Hanifa Garjistani? Hanifa Garjistani? Hanifa Garjistani? Bikal Gemeiri? Bikal Gemeiri? Laslan Gibbons? Lachlan Gibbons? Then Gursabijit Singh?
Yes, miss, I'm here.
Thank you. Kashem Hassan? Kashem Hassan? Daniel Egi? Daniel Egi?
I'm here.
Thank you. Riha Jamshed?
I'm here.
Thank you. Benjamin Kahane? Benjamin Kahane? Benjamin Kahane, Azim Khan, Grishmi Khanal,
Yes,
Grishmi
ma'am.
Khan,
Yes, ma'am. Yeah, I'm here.
thank you. Manali Kerudia,
Yes, miss.
thank you. Agatha Kosinska,
Here, miss.
thank you. Kukule Kankan, Shanchit Kukule Kankan, all right. Dufeng Luo,
Present, miss.
thank you. Prithviraj Matra, Prithviraj Matra, okay, thank you. McAllister, Aaron
Yep.
McAllister,
Here.
thank you. Ayush Mishra,
Yep. Present.
thank you. Nasrallah, Abanub Nasrallah, Nil Patel,
Yep, present, miss.
thank you. Pearson Borne, Rohan Pearson Borne, Austin Paris,
Yeah, I'm here.
thank you. Pirapinthan, Anushka Pirapinthan,
Yes, miss. Yes, miss. Yes, miss.
thank you. Morshed Rahman, Morshed Tanjim Rahman, Muhammad Ali Raja,
Present, miss.
thank you. Yusuf Rifat, Yusuf Rifat, and Olivitas Rodrigo,
Present, miss.
thank you. Jacob Rodriguez, Jacob Rodriguez, Brandon Rogers,
Here, miss.
thank you. Ozzy Sadiq, Mohammad Sadiq,
Yeah, I'm here.
thank you. Sabita Shahimahol,
Yes.
thank you. Abhinav Srishta, Pranil Van Singh,
Yeah, here.
thank you. Mutasim Tai, then Tomena, Nourishna Tomena, Nourish Tomena, Min Nahat Tran, Zhao Ong,
Yeah, I'm here.
thank you. Jijiang Jiang,
Yeah, I'm here.
thank you. Tamara,
Here.
thank you. Ali Ahmed,
Yes, miss. Ali Ahmed here.
thank you. Nilufa Afrin,
Yes, ma'am. I'm here. Thank you.
thank you. Abu Huraira,
Abu Huraira, yes, ma'am.
thank you. Orpita,
Yes, ma'am.
thank you. Amir, okay. Piti, Laura, all right, thank you, everybody. Is there anybody left behind?
Hello.
Can you please?
Yep. Ben Kahani.
My microphone wasn't working before.
Okay, thank you.
Cheers.
No worries. Any other?
Excuse me, miss. Me too. Abhinav Shrestha.
Abhinav Shrestha? Yep.
Yes, thank you.
Okay, no problem. Okay, thank you. Bye.
Okay, thank you, everybody. So that's the end of the lecture. I will. Is Salah here? Salah Darwisi?
Yeah, I'm here, sir.
Okay, so I'll send you a new Zoom ID.
On my email or
in
on
your
the Zoom?
university email. Your student
Okay.
ID is 19379454. Is that right?
Yes, sir.
I'm
Thank
sending
you.
an email creating a new Zoom ID. And Saika,
yeah, Prof.
I think you need to attend to it as well because since you have done the marking.
Okay, Prof.
All right.
Thank you. So that's the end of this lecture.
Prof, you will send me to the link?
Of course, yeah.
How are you, sir?
Okay, thank you. Bye.
Yeah. Any question?
Yep, sir.
Yes.
I had issue with the mark for the exam. It was 4.5 and now it's 38.
So it was 4.5 and then now it's 8 or something, you mean?
38.
38.
Yeah.
So before it was 45.
Yeah.
Now it's 38.
Yeah.
So you want to talk with me as well?
Okay, sir.
I have to organize a special meeting because we cannot discuss one student's exam paper with another student. So Sinan Bayu. So yeah, Sinan. So I'll send you a Zoom ID.
Okay, sir.
So let him. So if you want, let him join our one. So it doesn't really matter.
No, I cannot do it. I cannot break the rule of the university. Unfortunately.
Okay.
I'm not allowed to do that. Yeah.
So each student separately, sir?
Separately, of course, it has to be one-to-one discussion because we have given general feedback to everybody, which is fine.
Okay.
But when you have a specific thing, a specific issue, then we cannot do it in front of the other student.
Even if I give permission, or?
No, it's not your permission. In the university, we are not allowed to do it.
Okay, no worries. Thank you, sir.
Okay, so I'll end this session now, and then I'll send you the Zoom ID, the 2 students.
All right, thank you,
Sinan
sir.
And Salah.
Okay, are you gonna do it now, sir?
Thank you very much, sir. Thank you.
Yeah, I'm sending it. Give me 1 or 2 minutes time because it will take time, a little bit of time to send it.
Yeah, no worries, sir. Thank you. We're waiting. Thank you very much.